Okay, welcome back to another MECH 1000 video. We're looking at Unit 9 in the Blueprint Reading textbook, which is about threaded hole specifications. Now we were a little bit rushed for time at the end of the last video. I had to quickly finish this problem from this example exercise, and it was just asking for the distance, center to center distance, between the hole with the counterbore and the one with the countersink. And so we found the horizontal distance and the vertical distance using these given dimensions, and then used Pythagorean theorem to find that. And I actually came up with an answer that is 1/100th of an inch off from what the PowerPoint here says. So I can only imagine that this is some sort of typo. I don't see any mistakes I've made here, but it's really not that big of a deal. The main point here I want you to learn is how to read these types of ordinate dimensions, how to use them to find distances, and also just a reminder of how to recognize the countersink and counterbore symbol. So the actual mathematics of finding that distance are not quite as important as the concepts of reading the dimensions and reading the symbols being used. Okay, let's get back to a more conceptual question here. What class of fit is specified for the tapped holes? So that falls right in line with the threaded hole specifications that we're learning about in this unit. And so we need to find a tapped hole. And actually, if we find all of our tapped holes, here's one hole note, here's another, and you'll notice that they all have 2B, 2B, and 2B. So that 2B indicates that the B means that they are internal threads inside a hole, and the 2 is the class of fit. So these are class 2, which is the standard default class. What is the thread depth of the blind hole? So we can see in the right view here that there's the blind hole, okay, which means it's this one over here in the side view. And so we can see there's a lot of information here. We need to kind of parse this out. We've got number 3 hole. So the hole itself that goes through the block, or it doesn't go through, it's blind, but the hole itself is a number 3 hole, which corresponds to 0.213 inches. So that's drilled. That's the drill that's used for the hole. 0.75 plus or minus 0.06 depth. So that's a depth, but that's the depth of the hole itself. In addition, the hole has a 45-degree chamfer, and the chamfer is made until the outside chamfer diameter, the outside circle there shown with a continuous visible line, has a diameter of 0.28. Then we get to the threads. 0.250-28 UNF-2B. That's the thread specification, and the depth of the threads is 0.62 minimum depth. So the depth of the hole is 0.75, but the depth of the threads is just 0.62. 0.62 minimum, we should say. That's the minimum depth. So it could be deeper, and that would be okay, but it needs to be at least that deep. Is the tap drill smaller for the fine thread or the coarse thread? So again, we need to look at these 3 hole notes and see what types of threads are being specified. Here we have UNF, that's fine. UNC is coarse. UNEF is extra fine. So the question is asking about the coarse threads versus the fine threads. What tap drill would be used? So this has a number 3 tap drill. This has a number 7 tap drill. So we can't just go by 3 and 7 and say, oh, well, 7 is bigger than 3, because it actually goes the opposite way. The bigger the number, the smaller the actual size. Now, luckily, we don't have to look it up on a chart. We can actually see it's given right here inside these parentheses, 0.213 versus 0.201. And so the smaller one, the question is asking for which one is smaller, would be the number 7 tapdro that's used for the coarse thread. What TPI is specified for the fine thread? So UNF is fine, 28 threads per inch is the TPI. And that's what TPI stands for, threads per inch. What is the pitch of the extra fine thread? So we haven't calculated this yet, but we have down here is our extra fine thread, and it has a TPI of 32. TPI is 32. So that means that there are 32 threads per 1 inch. We want to know the pitch, and the pitch is basically the size of one thread. So if we have 32 threads fit into 1 inch, how big is just one thread? So basically what we need to do is just flip this, find the reciprocal of that fraction. So instead of 32 over 1, it becomes 1 over 32. That's the size of one thread. So you can imagine if each thread is a 32nd of an inch, and we have 32 of them back to back, then that's going to be 1 inch long. So that is the pitch. And 1/32 of an inch, written as a decimal, is 0.03125. Now, up until now, all the threads we've talked about have been internal threads, threads that you find on the inside of a hole. But the reason why we put threads inside a hole is so that we can screw a fastener into it. So that fastener, that bolt or screw, has to have threads on the outside of the part. And so those are the external threads that are going to correspond with the internal threads inside the hole. They are labeled in the same way, the same type of designation, same type of thread specification, except we have one additional method of graphically representing them. So our internal threads can be shown as simplified or schematic, and we can still do the same thing for our external threads, but in addition, we have the option of showing detailed external threads. So here is an example of detailed threads. So this is really the most of the 3 ways of showing threads. This is the most accurate. This is the most realistic. We've got both right hand and left hand examples there. Of course, this is the schematic. This corresponds with what we saw earlier for internal threads and the simplified method. So rather than having the dashed line on the outside of the hole, now we see the dashed line on the inside of the fastener, the inside of the visible line, showing the edges of that fastener. Okay, so here's an example of some external threads being shown with the schematic type of representation. Oftentimes, fasteners, bolts, screws, they do have a chamfer at the end. That chamfer helps with assembly. And they may have a neck as well to allow for flush mounting of the head against the surface upon which the hole is drilled. So again, we see the specification here indicating the major diameter. So this would have a diameter of 0.5. 0.500. 13 UNC, 13 is the TPI, threads per inch. UNC is the form and series course. And 2A, so 2 class of fit. A means external threads, and it indicates the length of those threads along the fastener as well. Okay, so we showed earlier the basic shape of unified national. It had, I believe this was a 60-degree included angle between the threads, and it had flat tops. And this is what we primarily use for fasteners in the US. It's a combination of 2 older thread forms used in the US and Britain. But it's not the only kind of thread we might see. You might see square threads for power transmission, like in a bench vise. We've got Acme threads that have both a flat top and a flat bottom. Buttress shaped threads are used for transmitting power in just one direction. So these would be used maybe in a type of machine with some sort of maybe drive screw that only turns in one direction. Knuckle, these rounded type threads, can be found on light bulbs. And sharp V threads can be used for pipework, where you want full contact between the internal and external threads. This is what the old British Whitworth threads looked like. They were rounded at both the top and the bottom. And there's the buttress threads again. Okay, so I'm not really a big fan of these little animations that the publisher tends to throw in, but so just ignore that for now. I have no idea what that has to do with anything here. But what is the diameter of the material specified? So again, I want to remind you that sometimes the information we're looking for is not found in the drawing, but instead in the title block. So the material that was used to make this test shaft was a 1 3/8 inch diameter piece of stock material. So 1.375 is the answer. What center drill number is specified? So we haven't talked about center drill. That's right out here. Center drills are used when you're putting something onto a lathe, when you're turning it on a lathe. And so that's what the center drill is. And we can see here from the specification, it's a number 4 center drill on both ends. So that answers number 4. What neck diameter is required adjacent to the thread chamfer? Okay, so in this drawing, threads are shown using the simplified method. These dashed lines here are indicating where there are threads, and the end of the threaded portion is chamfered, and beside that we have the neck. So first thing to do is just identify what is the neck and where is it. There it is. And then we want to know the diameter. That's actually shown here in the partially enlarged view. 0.69 diameter. It's telling us what that diameter is at the neck. How many full threads will the threaded portion contain? So I'm looking down at my timer and I'm down to less than a minute. I don't know, this problem might take me longer than that. So I don't want to be rushed, and I want to get all the way through this. So I'm going to stop the video here, and we will answer this question in the next video.